So in section 5.3 and section 5.4, we're going to be dealing with a multiplication rule instead of an addition rule. So we've talked about addition rules, now multiplication rules. The difference between section 5.3 and 5.4 is going to be whether or not we have events that are independent versus dependent. So the first thing that we have to do is talk about what it means for two events to be independent from each other. So I'm going to start that with an example that kind of illustrates independence, okay? So take a look at this first example. Suppose a coin is flipped twice. What is the probability that the second flip will land on heads? B, suppose two cards are drawn from a standard deck of playing cards. What is the probability that the second card will be a king? So here's the deal with the first example there. So I'm going to flip a coin 2 times, right? So I'm going to flip the coin and, you know, maybe I'm going to even not show you if it's a heads or a tails on the first flip, right? And then I'm going to flip the coin the second time. And the question is, what's the probability on the second flip it lands on heads? Well, on the first flip, if the first flip lands on heads, what's the probability the second flip will also land on heads? So if the coin lands on heads on the first flip, the probability that the coin lands on heads on the second flip is still 50%, or 1/2. What if the coin landed on tails the first flip? What's the probability it's going to land on heads the second flip? Still 50%. So the point is, what happens on the first flip doesn't affect what happened on the second flip. The probability of heads on the second flip is equal to 1/2 or 50%, regardless of what happened on the first flip. New question. Suppose 2 cards are drawn from a standard deck of playing cards. What is the probability that the second card will be a king? So visualize this, right? I shuffle my deck of cards. I'm going to draw out 2 cards. So I draw out the first card and I lay it face down on the table. And then I'm going to draw out a second card. What's the probability that the second card is a king? It depends, right? It depends on what that first card was. If that first card was a king that's laying face down, then the probability of the second card being a king would be 3 out of 51, because there would only be 3 kings left in the deck that I could possibly pick on the second card. And there's only 51 cards left that I could possibly pick on the second card. But if the first card is not a king, then there would still be 4 kings left out of the 51. So the answer to this is that it depends. So the probability the second card will be a king is, it depends. It depends. If the first card is a king, then the probability, I'm just going to say then, it will be 3 out of 51. If the first card's a king, then there's only 3 kings left, and there's only 51 cards left, so it would be 3 out of 51. If the first card is not a king, then it will be 4 out of 51, because there would be 4 kings left in the deck if the first card's not a king. So what I'm getting at is the difference between independence and dependence. In the first case, the first flip and the second flip are independent of each other. It doesn't really matter if you get heads or tails on the first flip. The second flip is still going to have a 1/2 probability, either way. But on the second scenario, when I'm drawing out two cards, the probability that the second card is a king depends on the outcome of the first card. As we just saw, if the first card's a king, then the probability is 3 out of 51. If the first card's not a king, then the probability is 4 out of 51. So two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. So whether or not event E, if it occurs or not, that does not affect the probability of F. If that's the case, then the two events E and F are independent from each other. So again, the first flip and the second flip are independent of each other. The second flip is not affected by the outcome of the first flip. So in other words, the probability doesn't change for the second flip, no matter what the outcome of the first flip is. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So again, first card and the second card in my second example, those are dependent events because the probability of the second event depends on the outcome of the first event. The probability of the second card being a king depends on whether or not you got a king in the first event, in the first card. So I'm going to skip this just for a second, and I'm going to jump down here to the multiplication rule. But before I do that, I do want to point out that it is very, very common for people who are first sort of studying the idea of independent and dependent. And we just previously talked about the concept of disjoint. It's very common for people to get those two concepts confused. And so I want to point out to you, you really need to pay attention to the difference between those. They're not the same thing. Two events are disjoint if they can't both happen at the same time. Two events are independent if the occurrence of the first event doesn't affect the probability of the second event. They're not the same thing, so you got to make sure that you are keeping those straight. Typically, you're going to be concerned about whether two events are disjoint if you're going to be looking at the addition rule. If you are worrying about whether or not two events are independent, that's going to involve a multiplication rule. So our multiplication rule, if E and F are independent events, then the probability of E and F equals the probability of E times the probability of F. This is the multiplication rule for independent events. We're also going to have a multiplication rule for dependent events in the next section. So it's important to recognize this is the rule if we have independent events. So suppose a coin is flipped twice. What is the probability that the coin will land on heads both times? So in other words, what I'm being asked here is, what is the probability I'm going to get heads on the first flip and heads on the second flip? So if it's going to land on heads both times, then the first flip's going to land on heads and the second flip's going to land on heads. Since the first flip and the second flip are independent of each other, I can find this probability just by finding the probability of heads on the first flip, finding the probability of heads on the second flip, and multiplying those two things together. Well, the probability of heads on the first flip, 1/2. The probability of heads on the second flip, also 1/2. So the probability of heads on both flips 1/2 times 1/2 is equal to 1/4. We have a 1/4 probability, if I flip a coin 2 times, that it's going to land on heads both flips. So this multiplication rule allows me to figure that out relatively simply because the 2 flips are independent of each other. Sidebar. Another way that I could figure out this probability would be by listing the sample space. So when I flip a coin 2 times, there's 4 possible outcomes. It could land on heads, 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 tails, tails, heads, tails, tails. So this is the sample space. Now, of the sample space, there's only one way that we get heads both times. And so there's 1 favorable outcome out of 4 total outcomes. So we have a 1/4 probability. The benefit of the multiplication rule is that I can figure out this probability without having to list the entire sample space. Before I move on, the author has a note in the book that I included here about disjoint events versus independent events. And again, the point is that they're not the same thing. Disjoint events and independent events are different concepts. Recall that 2 events are disjoint if they have no outcomes in common. That is, if knowing that one of the events occurs, we know that the other event did not occur because they have no outcomes in common. Independence means that one event occurring does not affect the probability of the other event occurring. Therefore, knowing 2 events are disjoint means that the events are not independent. So if we have 2 events that are disjoint, those 2 events have to be dependent events, because if you know one occurs, then the other can't have occurred, which means there's a dependence. That's not really the point, though, that I'm trying to make. The point that I want you to go away with is, first of all, make sure you're paying attention that there is a difference. Disjoint, they can't happen at the same time. Independent, one doesn't affect the other. And when I say affect, I mean the probability. We're worried about generally whether or not 2 events are disjoint when we have an or question. What's the probability of E or F? Then we worry about whether they're disjoint. Can they happen at the same time? When we worry about independence, it's usually going to be an and question. What's the probability of E and F? Are those 2 things independent or not? Also, when it's an or question, we will typically be using the addition rule. When it's an and question, we will typically be using the multiplication rule. But even that's not going to be foolproof. Usually when we are dealing with like whether or not 2 events are disjoint, there's going to be a single action. So like I'm going to draw 1 card. What's the probability it's a king or a queen? A single action, 1 card. So I worry about whether kings or queens are disjoint or not. When I'm worrying about independence, there's usually multiple actions. I flip the coin twice. So you have the first flip and you have the second flip. And so that's generally going to be an and question, and we're dealing with multiple actions. The exception on the and would be like the problem that we had right here. What's the probability that for a married couple selected at random, the couple has 2 or more children under the age of 18 and both spouses work? That was an and question, right? But there was only a single action. So we were only randomly selecting 1 couple, and it's an and question. So in that case, we don't have to multiply or anything. We just had to find that there were 370 couples that fit that characteristic out of the 1,700. So again, what I'm trying to give you are some takeaways of how do I know when I add, how do I know when I multiply, and when maybe I don't even do either. So again, if it's a single action with an or, you worry about the addition rule. If it's a multiple action with an and, you worry about the multiplication rule. Now, the multiplication rule can be generalized. So what if we don't just flip a coin twice? What if we flip a coin 3 times or 4 times or 5 times or 10 times? Well, if events E1, E2, E3, and so on to En are all independent, then the probability of E1 occurring and E2 occurring and E3 occurring and so on and E sub n occurring is just going to equal the probability of E1 times the probability of E2 times the probability of E3 and so on until I multiply that by the probability of E sub n. So for example, suppose a coin is flipped 3 times. What is the probability that the coin will land on heads all 3 times? So in other words, I'm flipping the coin 3 times. I want to know what's the probability it's heads on the first flip and heads on the second flip and heads on the third flip. So because the first flip, the second flip, and the third flip are independent of each other, the outcomes don't affect the probabilities of the others. That's going to simply equal the probability of heads on the first flip times the probability of heads on the second flip times the probability of heads on the third flip. So the probability of getting heads on the first flip is 1/2. The probability of getting heads on the second flip, also 1/2. The probability of heads on the third flip, also 1/2. If I take 1/2 times 1/2 times 1/2, that is a 1/8 probability. So if I flip a coin 3 times, the probability that it lands on heads all 3 times is 1/8. Now again, we could have also have done this before by listing all of the outcomes. So the multiplication rule saves us from having to list the sample space. So for example, if I flip a coin 3 times, it could be heads on the first flip, heads on the second flip, heads on the third flip. It could be heads on the first flip, heads on the second flip, tails on the third flip. It could be heads on the first flip, tails on the second, heads on the third. It could be heads on the first, tails on the second, tails on the third. It could be tails, heads, heads. It could be tails, heads, tails. It could be tails, tails, heads, and it could be tails, tails, tails. So there are 8 different outcomes that are possible when I flip a coin 3 times. Of those 8 outcomes, one of them lands on heads all 3 times. So it's a 1/8 probability. If I didn't have the multiplication rule, I would have to do this problem this way by listing out the sample space. The multiplication rule saves us this headache.